So Bin Yu, who you see on the screen back here, but she'll come on there soon, is Chancellor's, she's our seminar speaker today, and she'll be giving a talk titled Interpreting Deep Neural Networks Towards Trustworthiness. She's a Chancellor's professor in the departments of statistics and electrical engineering and computer sciences at Berkeley. And she's a member of the U.S. National Academy of Sciences and fellow of the American Academy of Arts and Sciences. Her current research interests, and she of course can direct this, and we'll get to see more of this, are focus on statistics and machine learning methodologies and algorithms for solving high-dimensional data problems. Now, she's really been engaged in interdisciplinary research with scientists from genomics, neuroscience, and remote sensing. I recall her talking some years ago about how she was working closely with them, and her analyses were helping them decide which experiments to actually do. She's also, I know, out a really big project at Berkeley focused on theoretical foundations of deep learning. So I'm sorry you couldn't be here in person, but we're really happy that you can join us now. And so thank you, Ben. Oh, now I see you there. Thank you very much for joining us.
Thank you for having me. Sorry, I cannot be there.
So we have about 30 people in the room. They're a mix of undergraduates, graduates, postdocs, faculty. So that's who you're speaking with, right? Thank you.
So I have 40 minutes, is that right?
I think you have an hour.
Okay, that's good to know. That's even better. Okay, so since I'm not there, it's kind of hard to see the audience. I really encourage the audience to ask questions. I think I'd rather have a discussion than just go through my slides. So do please raise your hand. So,
right. So I'll try to keep watching. If you want to ask questions, I'll try to get your attention so you can answer the questions.
Yeah, I'd rather have a discussion. I think it's more fruitful than just going through my slides. And
okay. All right.
Especially if many of you come from mathematics, I haven't been giving talks to mathematics people for a long time. So do please interrupt me if you think that I'm not making sense to you. So I really appreciate that. Okay, thank you for the introduction. So what I want to do here, just share a sequence of projects my group has been engaged in, and ranging from more machine learning, generic machine learning interpretability to scientific investigation with cosmologists and cellular biologists. And also there's some general framework which we have been using, more like the research philosophy my group has been following. And so it's pretty, I'm trying to cover a really wide-ranging topics, and have some feedback from the audience would be really helpful. So everything's being called AI, right? It's a different discussion about what's really AI, but one thing for sure, algorithms, data are entering every aspect of life. And I like this quote from Bill Gates: AI is like nuclear energy, both promising and dangerous. Data science is at the heart of current AI, well, together with hardware and database and other things. But I would think the brain of AI is really algorithms with data and domain knowledge. Really, we need all three components. I don't believe that abstract algorithm will solve all the problems, but generic off-the-shelf algorithm can also help us start, but we really always have to use domain knowledge to have some reality check, both quantitatively and qualitatively. And data science is done by people. It's not abstract somewhere in the clouds, and just this huge involvement of humans in this data science lifecycle. And in my world, it's my group, and also my many collaborators from cosmology, cardiology, Drosophila biology, and cellular biology, and neuroscience. So I want to put people at the center and recognize that we're not robots. We're making many human judgment calls, sometimes good, sometimes bad. And we need to recognize and find ways to evaluate and vet these human decisions. So a lot of us traditionally have been working on the modeling and algorithm, the bottom node, right, in this cycle. So I want to use that. I don't know how much you guys know. There was really a great period in statistics, probably after the war, which is quality control, right? That was really drove the Japanese car industry and later also American car industry. It's really this idea that you need to really monitor the process. And when things, the 2 sigma or 3 sigma rule is off expectation, and then some human intervention needs to be done. This is more like factory floors. But now AI is also entering factory floors, and we data scientists actually go through these different steps in our office and labs, not in the factory floor, but the thinking philosophy still make a lot of sense, is we need to quality control. Most of us work traditionally in this modeling and algorithm aspect, right? We use notations in code, in mathematical proofs, and we often just disappear in the notations. But we really need to take a step back and think about the whole data science life cycle. Even we do work with notations, which can be very, very useful, but if the notations, the symbols, don't have reality correspondence, all the beautiful theorems we prove has no reality bearing. And the conclusions doesn't naturally just work in practice. We are mathematicians, we always prove theorems, and we always have conditions. And how do we know these conditions actually hold in practice? And that part cannot be done by more manipulation notations. That's done by narratives, by talking to people. You make a case, you have a story which is convincing using common sense domain knowledge, and that's why you bring X, a random variable, to life in the context. So now if I ask you, if supposedly I'm working with many doctors at UCSF, and in particular, we work with an ER doctor called Aaron Kombloth. And we've been using a framework my group developed called PCS, Predictability Computability Stability, to really evaluate existing clinical decision rule. So this decision rule is used by doctors across the country, ER doctors. When a child comes to an emergency room with, say, abdominal injury, and this decision rule is supposed to, you have to collect some data from, ask questions and things that check whether there's tenderness at the injury spot, and then a decision has to be made whether to send this child to a CT scan. And CT has radiation. And if it's not necessary, you don't want to over prescribe the CT to kids because the impact for their life when they're young can be tremendous. At the same time, you don't want to miss internal bleeding. That can be life-threatening right there. So it's really this trade-off between something called sensitivity. That means all the people who need to be sent to CT need to be sent to CT, and something called specificity. You want to make sure the negative, the people who don't need to be sent to CT, mostly are not sent to the CT. So you want both specificity, sensitivity and specificity to be high. So people have some organized, the ER doctors, pediatric ER doc organize themselves and have they studied the data called PCARM, and we're working with them, right? So if you think your child or your relative will be subject to this rule, I hope you all agree with me that you don't only want to worry about the modeling and algorithm stage or step in this data science lifecycle. You probably want to know how the problem, mathematical, statistical problem is formulated, how the data is collected, right? For example, one problem with data quality is that there's kids below 2 are not very verbal, right? So there's certain questions they cannot answer. One approach is that let's delete all the data from kids who are less than 2 years old, right? Because it's missing. There's this question this kid cannot answer. And you said, there's missing this, let's just remove. And then I hope you see that if you have a child less than 2 years old, whatever the development based on kids with data over 2 years old probably doesn't work. At least you should worry that it doesn't work. So that's about data collection and data cleaning, right? People can say, oh, there's another missing. There's this hospital seems to have a lot of missing values. There's data from another study with traumatic brain injury. There's data from UT Austin Hospital, UCSF, and Pittsburgh. Let's just delete all the data from UCSF. Say they have too many missing values, right? That's often done by people doing cleaning. But the population for that study, this is adults, in UT Austin are very different from UCSF. UCSF population patients are very diverse relatively, and UT Austin is very homogeneous, mostly Caucasians. So all of these decisions is going to impact on how generalizable your decision rules will be applied to all the hospitals in the country. And there's another problem, all this data cannot address most of the data collected in teaching hospitals. And teaching hospitals are very different from a random chosen hospital. So the question is, are this algorithm developed using data from teaching hospitals applied to a small hospital in somewhere in Wyoming? Because the doctors are different, they're trained differently. So all of this should concern you. There's no magic. So we're going to propose some conceptual framework for people to follow and document everything, all the human judgment calls. I hope I make a case that it's great. AI has a lot of potentials, but we have to be really, really vigilant to make sure that we're not causing harm, which is pretty easy actually. And a key for not causing harm actually is through interpretation. Today, I'm only concentrating on called post hoc interpretability, which means the model is already fitted. And I'll come back about the data process. So suppose you have a very rigorous process, follow the PCS principles and even more, and now you have a model you want to interpret, right? This decision rule we already made, the PCON group has made. We actually try to replicate, and we replicated their
Excuse me, Ben?
Yes.
So we have a question here.
Yes.
So I have two questions.
Take your mask down.
Oh, sorry. So I have two questions
Yes,
about the data science life cycle. I also learned that in school, but I was wondering, let's say you are a researcher in AI, and let's say, I mean, maybe you've been to the hospital before, but you don't really have expertise in that domain. Do you have to contact a domain expert to decide what things should be in the columns of your data set that you're going to use? Or do you maybe need to go and do your own background research to decide on that? And then my second question is, when you're trying to get—
Can I answer your first question first before you answer?
Yes.
The question? Yeah, that's easier for me to remember. Thank you. Excellent questions. Yes, there are two ways, as you said. For this PCON data, we actually work closely with the ER doctors. We actually went through every variable because there was an external study for two groups. We went through every variable together for the doctor to agree this variable means the same thing. And you can also read information about internet, but that's challenging. So in biological research, I watch YouTube video about biology. At the same time, I also talk to the experts, sometimes read textbooks. So all of that are valid approaches. But the easiest, the quickest is to work with the best doctors and the best scientists and pick their brain. That's the fastest. If you have good communication channel. It's just much faster. You can do interactive learning than passively reading. But for biology, I find much better to watch YouTube videos than reading books, because a lot of terminologies I cannot quite remember. But if I watch videos, I at least understand the mechanism, even without remember all the names of things.
Do you have another question?
Yeah, and my second question is about maybe it's kind of related to the first one, but in the data cleaning, data collection stage, I guess since you are taking data from different hospitals across the country or maybe across the continent or something, how do you determine, I guess, which variables to choose? And if they are as you were saying, differences in cultures, how do you decide how, let's say, how different A might be interpreted in culture, let's say A, and B might be interpreted in culture B. So let's say this might not be a practical example, but for example, let's say you have data on like temperature in degrees Celsius and temperature in, let's say, degree Fahrenheit. How do you like go about like bringing these two together? Even though like in the US it's Fahrenheit, but like how do you go about bringing two different variables that are similar together, but are used in a similar way in different hospitals?
That's another very good question. So for this PCON study, they have protocols to train the doctor to ask questions as uniformly as possible, right? So that's very well designed. And for other things, there's one big problem with MRI, right? We do brain MRI imaging, and not just cross hospitals, even different machines in the same hospitals are not always calibrated, or they might not be said the same thing. So it's a challenging problem. So what people do is they have these phantoms, right? You have like artificial brain or some sort of made up materials, and people carry that to go from hospital to hospital to get standardized measurements. But for other lab work, I think there's standards, but this is well known, effect, even from laboratory to laboratory, right? So you need something standard to calibrate against. And it's a very challenging problem. And the more rigorous people try to do the best they can. And for data processing, I think the measurement needs to be standardized. And that's why before the machine leaves the factory, right, there's a lot of standardization done already. But then when you go to the hospital site, MRI machine tuned by the radiologist, and people know that you don't go even the same hospital with different MRI machines, you might not get the same measurement. So calibration needs to be done, and it's not easy at all. And that actually creates problems with MRI measurements to do large MRI studies. Yeah.
Thank you.
Okay, thank you for the excellent questions. And EU now has another follow-up regulation to specify even more on those digital platforms, how interpretable things have to be. So interpretability is a key step in making things trustworthy, right? If we cannot even interpret things, how can you build trust? I mean, trust is not just rational. Trust is very emotional, right? For a human to trust something, it's not just a rational, but we hope we can use facts to build trust. But it's not 100% rational, for sure. Like the people you trust what they say, right? And where they trust, it's very complex. Here are just some examples. I mentioned about, medical imaging, right? You have a deep learning algorithm using computer replace a radiologist. FDA has to approve it, and they want to know how your algorithm does it. And I work with Drosophila biologists. It's very fundamental biology or basic biology that we want to know how these different genes interact to drive a phenotype, right? A particular size and things like that. And then we work with cosmologists and to figure out, they have simulated data about from the origin of the universe, Big Bang, to today, using something we can observe, use gravitational lensing technique. And they want to know why deep learning seems to work so well. They know it works well because they simulated the data. And then this is one way to establish which method to use for them to really estimate this parameter called the omega m with real observed data, right? And then there's this generic machine learning interpretability that we try to hope to solve a lot of problems with the generic same method. I'm more into, I think my group does both. A lot of the work we do, I would call interpretable machine learning and also scientific machine learning. So many people use the term scientific machine learning. Here's my definition. So scientific machine learning means that we use machine learning just like a statistical method for scientific research to extract from data using domain knowledge for discoveries. You can abstract theory and also build knowledge. At the same time, we can also build scientific principle like invariance principle from physical symmetry in deep learning models so that as a constraints work better than generic deep learning for physics. And it's a really iterative process, right? As I will show you in the next, in my 2 case studies, that you build in scientific knowledge, and then you also develop new algorithms, which can be used for other scientific problems. And I think scientific machine learning are subject to higher standards than machine learning because it's science. And we need to produce open source and reproducible software to support the enterprise of scientific machine learning. So at the heart of this talk is really interpretability. And this paper appeared 2019. And it's a attempt by my group, right? It was led by my 2 wonderful students who both, Jamie has left the group doing startup, and Chandon is graduating and probably going to work for health industry. And Risa is assistant professor at UCSF in neuroscience, and Carl is a postdoc at UCSF. So this group of people, I try to, since this is more like summer school, Jamie was into general machine learning, want to do generic stuff, very machine learning in philosophy. Chandon was pretty well trained already before he came to my group in neuroscience, but it's really super coder, very efficient like researcher. And Risa was the one who actually came up with the idea, said, let's do something because we have this different group of people in my group worry about interpretable machine learning. And then Risa actually came up with the idea that let's write a paper together. I thought this is a great idea. And Carl just being very, very thoughtful researcher who take it very, very slow, right? And doing beautiful work, but not worry about paper publication, just want to make an impact. So they're all very different. And our contribution is really bringing this relevance of the problem into the radar of interpretable machine. Usually you read machine learning literature, people just talk about generic. But I think it's very, very important for the current phase of machine learning. I would say the 2nd generation machine learning, we need to really root ourselves much, much deeper into the context, because that's where the big bang is going to happen. Big bang is going to be earned because the generic machine learning has reached, I think, a plateau, which solves a lot of problems. You need the specifics of the problem to guide you to revise your solutions so that to tailor make your algorithm by building in or bringing in relevance. So interpretable machine learning, we defined it as you have to have predictive accuracy. It's not absolute. So I was very humble in another project with cardiologists at Stanford. We could only achieve predictive accuracy of like 50% for binary classification balanced. I've never worked in such a weak signal case, but then we did follow-up experiment, knockdown experiment, and we did find things. So your predictive accuracy is not absolute. It's really relative to how much noise you have in the system. For biology, the system is much, much higher than finding a cat or a dog in an image, like what typically ImageNet does. So you want to have some sense whether you squeezed out enough information. And then you need a descriptive accuracy, whether the form is accessible by humans, right? Decision trees is very accessible, but I will tell you that wavelets are making case for physical scientists. Wavelets, Fourier domain is very accessible too. So that's where the relevance comes in. Your interpretable machine learning is for a particular audience, human audience, and to solve a particular problem. So the relevance. Most people probably agree with me, roughly speaking, you have a trade-off, but I will show you not always a trade-off. Sometimes you can improve both. People will say that, well, decision trees, especially small ones, like the decision rules I started with, it's very accessible, interpretable. And logistic regression, maybe linear, is the second one. And then random forest and deep learning become deep learning, especially with now the large language model coming out from the OpenAI and also Google and Microsoft. Billions of parameters. They're kind of black box right now. Hopefully we later can make them white box. But this is a general belief. Really the trade-off, it's about whether the analytical structure in your data has been adequately captured by a particular method you use. as I'll show you, you can often improve both. If you find the right analytical structure and then use that to interpret, and I can improve descriptive accuracy and also predictive accuracy. Sometimes you lose, but don't believe that it's always the case. It's really problem specific, context specific. As I said, this talk, I'm only concentrating on post-hoc interpretability, meaning that the data is already fitted. I assume that it's through a very rigorous process. And there are two kind of rough categories for interpretability, post-hoc interpretability. One is global interpretability. You're looking at whether this gene is important, whether the p-value is significant. Well, p-value I have another talk about. I think p-value used with caution, especially when the p-value is very, very small, you have a problem because all this analytical approximation normal don't really hold in practice with that degree when you look at small p-value, like 10 to the minus 17 or something. You just don't have the mathematical accuracy to trust it. So our PCS framework want to make a more robust version of testing hypothesis. So you have much small p-values, and then you can do visualization. And the local level is look at individual patients saying that I'm going to send this kid to CT. Here's why. She doesn't seem to be very awake, and there's something called Glasgow score, seems to be very not right. All of that, right? So you will explain to the parent, that's why this child is being sent to CT. And why do you trust the algorithm, right? Why, as a parent, if my child had to be sent to a CT, why do I trust, right? First, of course, we trust UCSF, the best doctors. And why these best doctors can be trusted is because they have been trained in the best scientific knowledge we know. So you hope that they already understand this decision makes sense to them, right? They're using it at UCSF, therefore, all these past centuries of accumulation of scientific knowledge got training into their medical school training, and they look at the decision rule, makes sense to them, right? That's implicitly making that assumption. And the other thing, which will be very, very hard for the parent to know, is how this data was collected. And that's why, as data scientists, we have to make sure this process is legitimate, right? Even sometimes you can come up with reasonable decision rules with completely crappy process, and you shouldn't use it because you need to be factual and you let the data speak for itself. Or you should just say, I believe that, instead of saying that it's data-driven. And that's, at least, it's false advertisement. Any questions before I dive into the details of the talk?
Yeah, I think they're okay for you to continue. So
Okay. So for the rest talk, I'll start with generic machine learning approach, started by Jamie Murdoch. And then with my pushing, we went into cosmology. So we developed a generic interpretability machine learning technique for deep learning called ACD. And then worked pretty well for cosmology. And in the context of cosmology, because the free domain is very meaningful for the cosmologist, we start thinking about we should do local Fourier transform, which is wavelets, and we want to do data-driven. So that drove a new methodology, right? See, we start with generative methodology, and we went in with something, right, to tell the cosmologist, we want to try this on your method, on your problem. And then in the context of cosmology, free domain thinking made us want to do, and also my own research from 20 years ago or 30 years ago on wavelets. It's also a driving force. I love wavelet. I think it's a beautiful mathematics and very useful. And therefore, we developed a new methodology called adaptive wavelet distillation using deep learning. And then we now want to solve another scientific problem in cellular biology. So you can see the interaction, right? The iterations. And now it's a general methodology. And for me, I always want to find another case study to make sure this general methodology not just solve a particular problem that you develop for, but another problem. And then I'll end with the general framework. how to make our data science lifecycle to be as kosher as possible. This is a general machine learning thinking, right? Jamie is a general machine learner. And we look at the interval machine learning when we started the project. People, if you look at science, a lot to do with perturbation, right? Who is a scientist? Scientists tune this, tune that, and see what happens. It's about perturbation to a system. Biology does it, physics does it, and material scientists does it. So this perturbation idea is our intervention with the universe. It's also built into interpretation. So here, as machine learners, we kind of use the object, which is a big machine, like deep learning model, which it's very complex already. We perturb it, right? So you do local perturbation as a fitted value, you do gradient baseline or integer gradient, or you take a certain parts out, and even sometimes after a fitted model like sharp, but you're doing perturbations. So this is a key idea, which is very, very prevalent in science and in interval machine learning. So, but what happens is that in the sentiment and then the movie is good, right? It's positive. Existing work when we started only gave attributions of importance to not and good, but not to not good. So we set up looking at the literature and saying that, hey, there's a need to give also importance measure of some sort to not good. So compositional importance. That's what set Jamie on this path to build on other people's work, but go the next step. Because a lot of times it's by interactions, not just by individual. The words individually especially mean something very different when you combine them. And so this work called contextual decomposition started when Jamie went to work with Liu at Google Brain, I think probably 17 and 18. And then I joined the project. So Jamie was able to take a look at the inside of a fitted deep learning model. And I should just say that take apart, I want to give an importance measure to very good. And I take it apart into the original input into very good and not. And then I trace, this is actually some quite complex looking formulas. I trace the propagation when you feed forward to get a prediction out through the many layers of deep learning, started with LSTM. And we force some additivity. The paper will give you, this is Aclair paper 2018, will give you some number we call CT score for the very good part of what we care about, and then a not part. And later we generalized to also images with Chen and Singh. So this is the paper where we generalized. But this paper not just generalized. So now so you have not very good. So you have all these numbers floating around, right? Any compositional phrase, you get a number. But they're not really humanly interpretable if you just give me this list of numbers about importance. We need to organize them in a more accessible way. So this is the paper, Aclair 2019, and Chen and Singh joined the project to use a hierarchical clustering algorithm by using the CD scores to combine and to make them into a tree, which is more accessible. So now, instead of just, we have 5 numbers here, we organize the 5 numbers into interval form. So the lower layer is the words, and then the color, the blue means positive, and the shade of blue means how positive it is. And then we say that, well, if you combine very good, you have the biggest jump. So that's when we combine them. That's so important. And then become very good. And then, but you put in not in, the label flipped. So this really explains why not very good is labeled as a negative sentiment. And you see how the algorithm does it. And you can do more complex ones. And you can do similar things for images. And then it's like, well, you said, looks interesting, not very good. That example seemed to convince me, but I have thousands of sentences. How do you know I should trust all of them? That's a very good question, right? You can say that my interpretation, just an illusion, and you're just cherry picking. People often do that. Things seem to make sense. So we run a human experiment with random examples from this different data sets, right? So this gives you a sense that we're not cheating. So the first experiment is a small experiment with 11 people, but still better than just the researchers who do it themselves. So SST is the Stanford Sentiment Trunk. It's a text like sentences, like Yelp reviews and things like that. MNIST is the digits. And ImageNet is about different 1,000 categories of like cats and dogs and things like that, and birds. And the first experiment, we compare 4 different methods. One is ours, ACD, and the next one is also our CD with our organization, and the other one are two existing perturbation-based methods. So what we did is that for random selected sentence, right, and you have this LSTM, it's a recurrent neural network, and we randomize some of the weights, make into a corrupted model, but we randomize in such a way that the label is still the same. So it's positive, still being labeled positive by the fitted model. So now you created a good model and corrupted model. And then the interpretation take into account this weights. So we hope the corruption will get reflected in our importance measures. So we give the interpretation of this sentence, say not very good, and corrupted version of not very good model to the same human subject and say that which one makes more sense to you. If they can tell using the interpretation, because using human knowledge, then they get accurate. So you can see that they were able to use our method to tell a good model from a bad model using the human knowledge, what makes sense, with like around 70%. And the 2 other methods below 50%. And MNIST seems like everybody works okay. And for ImageNet, you can see even our individual method without the organization also doesn't work because there's too many numbers. And you can see the other 2 methods work slightly better because they don't have as many numbers because they only do marginal interpretation. For us, is that we have, for pixel level, we have a group of pixels. You can see just very overwhelming unless you organize it and then you do better with the dark blue bar. On the right, the experiment is something different. It's just that I'll give you 4 different interpretations from the 4 methods. Based on this interpretation, do you trust the model, right? Because that's where we build the trust, right? Through the interpretation, because we cannot look at it as a billion numbers. It doesn't make sense to us. So we have to turn this into something more accessible, still quantitative, but more accessible. And you can see that based on our interpretation, ACD almost crosswise except for MNIST, the other one, the dark, the light green bar works a tiny bit better, that our method comes ahead. So this is overall give us some confidence our method is meaningful and it's good, but I don't believe that one method works all the time. So I suggest you actually use multiple methods. The first theorem in statistical machine learning is that nothing works all the time. It's really to understand when and how and why they work. And then we also, with a visiting student from Dharma, Laura, we also use these scores and try to decrease reliance of, say, you don't want this result depends on gender, and we can reduce the reliance of algorithm on gender. So it's like use the interpretation to improve the model. Then I always wanted to do science and supported Jamie to do general machine learning, but my heart is always try to do science with machine learning and statistics. And so at the time, Francois Lanussi, the guy with the red sweater on the left, was a postdoc in the same grant as my other postdoc, Woo-Suk Ha. And so I said, why don't you guys work together to see whether our method actually works, right? Even we did a human experiment, in my mind, I still need more evidence how good our method is. So for me, it's like, I want to keep getting evidence our own method, because as I said, I don't believe it works all the time. I want to see the limitations and to also see where it works really well. And then we can tell people that I have confidence that it works for this case. And he brought into his cosmology project, Bohin and Liu. So now we come with ready-made machine learning tool for something which I don't really care as much as like sentiment analysis, ImageNet, to something serious, cosmology. So Francois already developed a deep learning ResNet for estimating a very fundamental parameter called the omega m. And they simulated this system from Big Bang expansion to current time, this purple image, which we can also observe with telescope, called the gravitational lensing images. Okay, so the idea is that with this made up simulation, we know the truth. We evaluate our methods. And this simulation, as known, physics is as good as science we can get, right? So it's as accurate as we can get. I'm sure they don't understand everything, but they understand a lot more compared with biology. So, and then ResNet worked the best. So the question is, why? How did this ResNet do it to beat all the other methods? We know the truth, right? So that's why we know that. And when we start talking to Francois, he said, you know, they look at things in the frequency domain. They don't do like the pixel domain. It's not very meaningful. It's the frequency domain. So because the relevance, we move to frequency domain, right? It's the science tells us that's where things are interpretable. So Fourier transform is invertible. So we just, if F is the ResNet black box, then if you do forward transform and inverse, you basically haven't changed anything. And you can put the inverse transform and F together, we have F prime, and we can generalize our method to also give interpretation for F prime. It doesn't have to be with a linear transform, we're fine. So because of that, we generalize our method, again, try to serve science, and we get a number out for each frequency domain, which is the blue curve. And this really says that about between 0.2 and 0.3 frequency band, that's where the data in that frequency is the most important for estimating omega m. And that's kind of where I think things are more or less Gaussian-like, and omega m is measuring really like some density, aggregated density of mass. And the high frequencies don't really matter as much. So this can be used by them to say they do simulations in the frequency domain, they can reduce the simulation in the high frequency because it's not very important for estimating omega m. And this is just some tau example to show that why we didn't use other methods. Even in this tau example, we really do much better, like 4% better. This is a very simple problem. Everybody does pretty well to find that breakpoint. Okay. So I always wanted to connect deep learning with Wavelet, something I worked on image compression denoising in the mid-90s. And I just thought Wavelet was just really beautiful theory and very useful. So I said, let's do Wavelet. I'll look at something called scattering transform early on, but Stanford Mallet's group developed, but we kind of drifted away from that. But this is another opportunity because Fourier domain is already, we should go to local Fourier domain, which is Wavelet. And then we also brought in another collaborator. We're already working with him, Yayula Gakko, for another problem for external validation, right? So this is the team was accepted last year, NERSC. So we have this ResNet model with 10 million parameters. Francois already developed, and try to make a huge model, gigantic model, small models. It's called distillation, and people still do that to find a smaller neural net model. And people also try to interpret decision trees and then editing models, because I hope the domain knowledge make them on this form is interpretable for them. possibly because this is the mathematical form fits our data structure. So, sorry, yeah. So what we want to do is actually improve interpretability, compression efficiency. And I was brought into the Wavelet work by two of my colleagues from Stanford who did a paper doing the statistical theory, estimation theory based on wavelets shrinkage. So what's discrete wavelet transform? Time series tie the time frequency domain vertically, frequency domain you tile this frequency time domain horizontally, and wavelet transform is tie them in a more smart way that you give less resolution to the high frequency because the high frequency is not usually in our life not that important, and you allow different frequency for different time intervals instead of just one frequency for everybody. And there are books by Millet and Mayer. And as I mentioned, this is a statistical work, a lot to do with mine going into data wavelets. I also love wavelet for another reason. I work on neuroscience. And you have beautiful Gabor wavelets mathematically made, and you look at first layer of AlexNet, actually they look very similar. So this is the physical reality I was describing, right? So you have mathematical entity, and you actually have physical evidence that's describing reality. This is based on data. This is nothing about mathematical modeling. They match. And there was also earlier work in the late 50s by two Nobel Prize winners, later got Nobel Prize, showed that if you have V1 measurements from cat neurons, V1 is the early visual cortex of our visual pathway, then the V1 neurons also act like wavelet filters, like have orientation selection, location selection, and also frequency selection. So all of this just come together, not because it's mathematically beautiful. The reason I love it is because also describe reality. So that's what I think I like most. Elegant and describe reality. If I have to choose today, I will choose reality over elegance, but I like to have both. It's hard to have both. I'll go for reality. When I was younger, probably I went for elegance. Now I go for reality. And then hopefully it's also elegant. So now we have a ResNet already fitted by the cosmologist with 10 million parameters. We can do the same trick as we did Fourier, right? Suppose we have a fixed wavelet transform, orthogonal wavelet transform, and there's inversion, and we can just do the same thing, and we can put the two things together, and we end up with F that we didn't use our ACD because it's too computation intensive. We actually used just the gradient. And we use the L1 of the gradient. So make a big function called F, and then you can calculate the gradient. So for any given wavelet transform, I can calculate this loss function. I'll explain. So the last term is the interpretation loss, use the ResNet. The first one just said, I want this transform to be almost invertible. And the middle term, I'll explain. For any fixed wavelet transform, I can calculate this. So we turn into optimization problem, want to search for a wavelet transform, equivalent in the mother wavelet. The H and G are the low pass and high pass filters for any wavelet transform. So we can optimize this. I'll explain what's the middle term in the next slide. And then we can find the really data driven. But we take into account the wavelet, not the wavelet, the ResNet, the deep learning in the last term. How do we make up the middle term? We look at all the equations in the books of wavelets and said, if you have a wavelet, these filters have to satisfy this equation. We turn every equation into a loss function, L2 loss function, to force to conform to be a wavelet transform. Otherwise, just get low pass high filter, who knows where they come from. And we just collect these equations and turn them into our loss function, the second term in our loss function. And I already explained the last term. Okay. And then we optimize. Use stochastic gradient descent. Actually, there's no stochastic here because we have no data. This is just a gradient descent. And this is just proof of concept. If you start with synthetic data, X and Y, which simulated some noise version of Wavelet. And we build a fully connected neural net, and we apply our method, we get the blue, which is data-driven or adaptive wavelet distillation, and then compare with the ground truth, you can see quite similar. And if you initialize this different existing wavelet works, but random initialization also works. Oh, the random initialization doesn't work, but we can delete the last part of our loss function and just find a wavelet and then run the full optimization with three-term, and that works. So it just says that it finds you what you start with. This is just say that depends on how you start. Things can be more better than other, but more or less you recover the wavelets. So the ground truth is WC5, and if you initialize with Kaufman 2 or SIM5, Kaufman 2 does better than the SIM5. So back to the cosmology problem, right? So independently, my suggestion to do wavelets, actually Francois also brought attention of wavelet to my team, because people actually, without knowing it, were already using fixed wavelet to do estimation omega m. And they developed a particular method called peak counting, which we're going to use. I'm not going to tell you it's already existing. So what we want to do is replace the fixed wavelet. They directly use cosmology mass maps and use wavelets and do peak counting. So our invention is that we start from these purple images, we build a ResNet, and then we distill the ResNet into wavelet and plug in the existing method people using for fixed wavelet. Okay, so that's our approach. We replace one step. We got data-driven, deep learning-driven wavelets instead of fixed wavelets. So if you look at the table at the lower part of the slide, you can see that AWD is our method. This is prediction error on a test set. We get 1.0 is 10 to the minus 2. Peak high is another method, much worse, 60% worse. And Laplace, you just use a fixed wavelet called Laplace, it's 30% worse. Robust cross, 25% worse. WC wavelet, 50% worse. ResNet, 15% worse. But the last row, the last number I want to draw your attention to, this is where you don't use the ResNet. You only use the first two terms, just find data-driven wavelets to feed the data. Then you get 30% worse. So ResNet is contributing. So we're able to reduce the number of parameters 10,000-fold from 10 million to 1,000. Okay, so this is improving prediction accuracy by 15% from ResNet and improve the number of parameters by 10,000-fold. So it's a huge reduction. Because my intuition said physics, wavelets is the right fit. Just structure in the data. That's why people develop Fourier domain, all this analysis. It's because in this domain, the structure fits the data, you have compression. And ResNet doesn't respect that. But ResNet did do the search for stochastic gradient descent, get us these fitted values that we need to do before we can extract good wavelets out. So we did use ResNet, but we end up with something much simpler. And if you look at optimization, remember I have two penalty terms and with two regularization parameters, and what we end up with, use cross-validation, we selected the red box one, which is a symmetric wavelet. And you interpret that as saying that you go to the wavelet domain using this mother wavelet. It's really measuring the difference of mass in the region of space with large densities and their surroundings. This is where omega m's information is contained in different resolutions, different locations, and you're collecting them and through the peak counting method. Okay, so this is one iteration, right? We start from generic machine learning method. We did something there pretty decent. And then we're not happy with it because we want to take the specifics of science into account and go to local Fourier transform. And we develop a new method and solve the problem. Before we only interpret. Now we not just interpret, we have interpretation also did better in terms of prediction. But I was not completely satisfied because I want to make sure this is really a general method, not just solve this particular cosmology problem. So we need another case study. That's where it comes a cellular biology problem. So the cellular biology problem, we're already working with SCOCO, the Advanced Berkeley Advanced Imaging Center, ABC. And this is a fundamental problem in cellular biology, something called cluster-mediated endocytosis. I didn't know about this process until I started working with SCOCO. Questions? No. So as this review paper says, it's a key process in vascular trafficking that transports a wide range of cargo molecules from the cell surface to the interior, right? We know that we have cells, right? And the cells need to bring things inside the cell. I always thought it was like ion channel, like open and close. But actually, no, this is more common than the ion channel. And I just read recently that, so for Omicron actually uses this process to get themselves inside the cell. But Delta and Gamma, the early version, use a different process called cell fusion. So Omicron became smarter and using the regular, more commonly used process to get into a cell. So how does this work? Suppose you have cargo, the little things, the molecule you want to bring, food or something you want to bring into the cell, right? It's the little like key-like things. And then there will be proteins, the little green guys, start tagging them inside the cell. The line is the cell membranes. And then the cell membranes will curve. And then there's another protein called actin will come in like scissors, cut it in, and the ball become in. But that's not done. Even the ball is in, this process is not finished because inside this ball, so you have to uncoat it, use another protein called oxalin. So this is called the cellular partner process we were asked to help. To see these two molecules work together. But the green one, which is have more information about whether the whole process is finished, is more expensive to observe. So we want to use the cheap one, which is the green clustering to predict. So that's a problem. Can we use the orange biomolecules intensity to predict whether this cargo is completely taken into the cell and be unpacked? So that's called molecular cellular partner problem. This is a way to understand this fundamental process. You have to observe things for disease. Maybe some of this is interrupted, right? But you have to be able to observe what's happening before you know whether this process is disrupted. So you look at the image, it's very grainy. Deep learning on these videos don't work. We couldn't make it work. And the videos actually is kind of funny, even for deep learning, you still have to do frame by frame. So we have to use a lot of knowledge, cellular imaging, to extract from the video data into a time series of intensities of the orange signal and the green signal. And then in the beginning, we have to use a lot of human engineered features because we didn't have enough data. Until we had enough data, we could feed LSTM, a recurrent neural network, with 1,000 parameters. And then we transferred the methodology from the Cosmology project and just code, right? This was not developed for the cellular biology problem. Because what I want to see is this is a general methodology, not just for the cosmology problem. And we distill. This is a very different network, very different context. And we distill wavelet. And then we took the top 6 largest coefficient at the top 5 scales. And we did a linear prediction for the green signal. And we improved both prediction accuracy and interpretation, right? So from 1,000 parameters, we end up with 30 parameters. And this is our score, so you want to be high. It's a proportion variance explained. AWE get 0.26, and LSTM get 0.23. So we get about another 10 to 15% jump in prediction improvement. And wavelets, it's worse. And if you don't use the LSTM, the deep learning model, again, you get just about the same. You can actually, for this problem, just do wavelet directly without LSTM. But the combination of wavelet and LSTM give the best result. So this is just, for me, we're very, very happy that this general methodology developed, we hope now has more evidence that called general methodology, because completely code transferred to a different scientific problem, which the method was not developed for. So for me, that I always at least needed 2 case studies. One is completely external validation. But you look at this wavelet, it looks different, right? The other one is symmetric. This one is really asymmetric. And it confirms what we know, right? We did a lot of work before we did deep learning with human hand-tuned features. We look at a lot of curves because relatively simple. You can look at that. This is really capturing, you need a large buildup in the orange signal, the clustering, and followed by a sharp drop. And that's the predictive of this whole cargo will be completely transported inside the cell. And this wavelet capture that, the rise and fall. Any questions before I go to the last part of the talk?
No, I think I'm fine, so keep going.
Keep going. Okay, so now I'll come back to where I started, like trustworthiness. One is to interpret the post hoc, the model fit, but I want to now advocate a framework we developed. My paper came out with my former student, now postdoc at UCSF, Concumbir, 2 years ago, called Veridical data science. Veridical means truthful, and it's really a name for the framework called PCS, Predictability, Computability, and Stability. So return to the theme of trustworthiness. Why is you look at the post hoc model and make it accessible by humans, and the human use domain knowledge to say, hey, this makes sense. That's needed. But also we need to make the whole data science life cycle to be kosher, quality controlled. And that's what this framework is about. It's really to summarize the best practices and build a platform for us to move forward and even improve what we have done. So to maximize the promise. I think when I teach undergraduate class, I think it's still useful even for myself, is that it's good to separate in our mind that the algorithms, the models, they are mental constructs. Reality is reality, exists independent of what your algorithm is. Your data is not reality. Your data is actually representation. So you have bad quality data, you have bad representation reality. So separate all these things. And my critique of classical statistics is that we merge everything together. You have the true model, you do maximum likelihood, and everything's fine. But in reality, it's never the case, not today. And also have future in mind. When you do this machine learning split, you need to keep the future in mind. And therefore, you should not split your data based on random split. When you have 3 hospitals, you should put a hospital aside, because most likely your future comes from a different hospital. So your test data should be the best surrogate possible within the data you have to represent the future. So keep who is going to use your algorithm in mind from the beginning. So as I said, in the paper, we define vertical data science as a data science extract reliable, reproducible information with an enriched technical language to communicate and evaluate empirical evidence in context of human decision and domain knowledge. What do I mean by enriched technical language? For deep learning, for example, we don't even have the term to describe what's going on in that high dimensions. So therefore, we cannot even understand, because without some language to describe what's going on, to communicate between humans, then we cannot even begin to understand what's going on. Again, back to the life cycle. We should really think about data science as like quality control process, have many, many steps, and every step has to be vetted, and every step has so many human judgment calls. We need to do stability analysis. So here comes what I mean by computability, predictability, computability, and stability. Predictability is taken from machine learning and statistics, right? But also for the PCS framework, it's also represent the future. you try to do something, predict something about the future. So keep future in mind, who's going to use your algorithm in what context, and then decide how do you set up your test data the best way possible to mimic that. Computability is no-brainer, but I'm adding computability on top of CS computability like memory, storage, speed, to actually data-driven simulations, very part of this framework. You want to use data-driven simulation to test your methods. Stability is really a significant extension on sample-to-sample variability in statistics to stability from the first step, right? When you have different discipline people talking about discussion, the words might not mean the same thing, right? Matrix for cancer researcher means a biological structure. To us means tabular data. So you have linguistic stability to start with from the beginning of problem formulation when you have multidisciplinary teams. If you don't have stability of language, you're going to have a problem doing the project together. And we do need to work together. And for data cleaning, right? And for data, there's so many public biological data sets. How do you choose the data set might change your conclusion, right? We have seen different random mild clinical trials actually can give you contradicting results on the same drug because they actually use different population. So all of that is stability issues. It's really fundamental. And even for data visualization, for one-dimensional data, now it's getting very popular via line plot. I still think box plot makes a lot more sense in more detailed information for me, because my line plot give you the sense that everything's so smooth and continuous, but a lot of time the outliers are not smooth, right? So all these choices will impact your judgment about your modeling stage. So you want to do different plots to see whether you colors, right? Red makes a difference than blue, all of that. We should record it through documentation and then really do manageable number perturbation and record the stability results. So I kind of went the path of advocating stability in 2013. And the PCS paper is expansion on my 2013 paper. At the time, I advocated stability as fundamental for interpretation and reproducibility, and argued that you need to do reasonable perturbations, and which was articulated more in the follow-up paper with Carr, that you need to do documentation to argue why this is reasonable. I hope you agree with me that stability is really common sense principle, right? If I want to be highbrow, you can quote Plato, a philosopher friend, suggested to me after I said somebody smarter than me must have something saying stability is useful. So here's what Plato said. For true opinions, as long as they remain a fine thing and all they do is good, but they're not willing to remain long, that means they're not stable necessarily, and they escape from a man's mind, we change our minds, so that they're not worth much until one ties them down, that means make them stable, and it's a more valued opinion. That's why knowledge is priced higher than correct opinion, and knowledge differs from correct opinion in being tied down. So this is, to me, says Plato says that things need to be stable to be knowledge. Of course, stability itself, it's not enough. Zero is very stable, but we're not going to report zero in every paper, right? So you need reality check. And then seek stability. So here's my attempt to show my students from last semester, mostly PhD master student from Berkeley, the importance. I've been teaching the class using the PCS framework to really see with their own eyes why I developed this framework, or we developed this framework. So 3 teams of students. With Aaron's help, we got 3 doctors work with them. And this is the PCON, not about abdominal injuries. This is about traumatic brain injury, the same consortium of ER doctors. And they also had already a decision rule. We try to reproduce that. The 3 teams cleaned the data differently. One team even cleaned away 23% of the data and got the best result on the clean data. And they did different plots. They used different methods, decision trees, and they even used different performance metrics. I thought it was clear from the paper the doctor had written that we should go for sensitivity and specificity, but some teams just went for predictability, didn't think about the context, and they reached different conclusions. So this is really showcased that this is a serious problem, that you need to do stability across teams, you can afford it, and really trust, basically have a multi-level human decision as teams to decide on what's the good clinical decision rule based on this, or take into account this variability. So all these variabilities, uncertainty well beyond the sample to sample variability traditional statistics discusses. These are uncertainties we need to take into account, and then we can do causal inference, PCS inference, which is a bit in the paper. We also did a genomics study of that. So give perturbation intervals. And the climate scientists are already doing that, right? I'm saying that don't just look at sample variability. You need to look at uncertainty introduced by different data cleaning and different methods. The climate scientist, we never see one curve to predict the global temperature rise at the end of the century. You see 9 of them. This is our called PCS perturbation interval.
Ben?
Yes.
Ben, it's Linda. So could you wrap up in the next couple of minutes?
Could I what?
Could you finish in the next couple of minutes?
Sure.
Okay, thank you.
Thank you. So we did stability analysis for our project, so I won't have time to talk. And the documentation is hugely important. You document what you did, the domain knowledge, the human judgment calls, and just make it a protocol. So working with different people to do that, to make it a protocol for my group, and also with different medical groups. So we did other projects using the framework worked very well. So hope you guys are willing to try out. And we have software to make the PCS style data analysis easy called Veridical flow. Go to my website code, and also have a sim shop to make simulation easy to have all the different perturbations. So hope you guys find it useful for your own data analysis. Future directions, we like to try understand better our prediction, like interpretation method, ACD and AWD. I don't think AWD works for all problems. For physical science problems, I think has an edge. And then we work with different groups, try to put the PCS idea into the different data protocols. And I'm finishing a book with my former student, current postdoc, Rebecca Barger with MIT Press. We're pushing to finish this summer and uses, this come from the 215A teaching and uses PCS framework. Start from problem formulation, data cleaning. I think maybe we are the only book I know that has a chapter on data cleaning, which is hugely important. And we don't talk about it. And we don't take into account the uncertainty there. So it's a big elephant in the room. We should really formally address that. And the multiple models. Thank you.
Thank you. Thank you.